Till now, we have discussed the recurrence formula for Bessel function and also the series representation of Bessel function. Now, today you will see that we will solve actually some important problems based on these concepts. So, I have selected in this regard these four problems which you can see. I have mentioned all these four problems here. So one by one we will solve these problems and you will find that the concept which we have developed in the previous lectures will be used in solving these problems. So let us see the solution of this first problem first of all, and for convenience I have again rewritten the same problem, that we have to show that j5 over 2 of x equal to square root of 2 over pi x times 3 minus x square over x square sin x minus 3 over x cos x. This result we have to prove. Now you can see this problem can be solved by using the recurrence relation. Particularly you can see if you will write the sixth recurrence relation which we have already studied, and I have suggested you to remember all those recurrence relations to solve this type of problems. So you can see the need of the remembering of those recurrence relations here. So you know that sixth recurrence relation regarding the Jn of x, we have already studied that this is 2n over x Jn of x equal to Jn plus 1 of x plus Jn minus 1 of x. This is actually the sixth recurrence relation. And from here you can easily find Jn plus 1 of x. You can see this will be simply 2n over x Jn of x minus Jn minus 1 of x. Now since we have to evaluate the value of j5 by 2 of x, so in this relation you can see since in LHS there is Jn plus 1. So if we put n equal to 3 by 2, then we will get j5 over 2 of x. So let us put n equal to 3 by 2 in this equation 1, which we have obtained by the use of sixth recurrence relation. So when n will be 3 over 2, you can see that this Jn plus 1 will be what? That will be simply j5 over 2 of x. And in RHS, we will also put at the place of n 3 over 2. So here at the place of n there will be 3 over 2. 2 and 2 will cancel. So only 3 will remain here. So this is 3 over x and Jn of x, and but now n is 3 over 2, so this is j3 over 2 of x, and here is Jn minus 1, and n is 3 by 2, so 3 by 2 minus 1, that will be 1 by 2, so this is j half of x. Now if you will put n equal to half, if we will put, you can see here in this equation 1, then this Jn plus 1 will be j3 plus j3 by 2, and in RHS n is now in fact half, so this 2 and 2 will cancel out and there will be only 1 over x, j half of x minus, and when we will write here at the place of n half, so 1 over 2 minus 1 will be equal to minus half. So now we have actually these two equations. You can see that is not two, but we have actually three equations. So now we will use the equation number 3 which we have obtained here in this equation 2. So you can see in RHS of this equation 2 there is a term containing j3 by 2 of x, and in equation 3 we have already obtained the value of j3 by 2 of x. So let us substitute this value of j3 by 2 of x in this equation 2 at the place of j3 by 2 of x in the first term in RHS. So after substituting it, what you will get, you can see easily. This will be simply j5 by 2 of x equal to, you can see when you will substitute here the value of this, so this 3 over x may be taken as a common factor, and j3 by 2 of x, this is equal to this much in accordance with equation 3, and the remaining term is minus j half of x, you can see here. So now let us simplify this RHS a little bit. So if we will multiply by this 3 over x to the terms inside this square bracket, the first term will be what? You can see this is 3 over x square minus 1 j, because you can see in the first term there is j half of x, and in the last term in RHS there is also j half of x. So actually I have taken this j half of x as a common factor, and we have associated this first term in the square bracket and the last term in RHS, and so j half of x has been taken as a common factor, and so this is 3 over x square minus 1 j half of x, and the remaining term is what? This will be 3 over x times minus j minus half of x. So this is simply minus 3 over x j minus half of x. Now let us take here LCM. LCM will be in fact x square. So this will be 3 minus x square over x square. And you have seen earlier in the series representation of Bessel function, we have already evaluated the value of j half of x. And I have suggested you to remember all those results. So you can see here there is a use of those results. In fact, in series representation, we have calculated the value of j half of x, and you have seen the value of j half of x is this much. This is a square root of 2 over pi x sine x, and minus this term 3 over x. And we have already evaluated this term also, j minus half of x. We have already evaluated in the series representation of Bessel function, and you have seen that this j minus half of x is equal to what? This is a square root of 2 over pi x cos x. So the results which we have obtained in the earlier lecture for j half of x and j minus half of x, we are actually substituting these two values in this equation. Now you can see that this factor 2 over pi x square root is a common factor in both of the terms. So you may take it as a common factor. So this will be a square root of 2 over pi x, and the remaining terms will be what? In the first term there will be 3 minus x square over x square sine x, and minus in second term there will be 3 over x cos x. And this is the result which we have to prove. So you can see such problems can be solved only when we remember the recurrence formula and the results of the series representation. If we are not remembering this formula, then solution of such problems will be very lengthy, because in fact in that condition you have to obtain all the results again, but that will be not convenient. So definitely you should remember the recurrence formula and all the standard results we must remember to solve the numerical problems. And such types of problems are actually asked in various competitive examinations and your academic examination too, so you must remember those. Now you can see I have mentioned here the second problem. The second problem says that d dx x jn of x times jn plus 1 of x is equal to this much. In fact, this result we have to prove. So now let us see how we can prove this result. Actually, this result will be also proved by the use of the recurrence relations you can see here. So now let us start with the LHS. So solution of this problem will be what? This is d dx x jn of x times jn plus 1 of x. In fact, to put this result in a convenient form so that the recurrence formula may be used, I am rewriting this expression in this way. You can see this may be written as d dx, and here I am taking a factor x to the power minus n. I am taking it, jn of x. But since in our result there is only x and I have taken x to the power minus n, so you can see if we will multiply by x raised to the power n plus 1, then result will remain same, because x raised to the power minus n times x to the power n plus 1, that will be simply equal to x. So instead of this x, I have written x to the power minus n times x to the power n plus 1. And the remaining factor is what? The remaining factor is jn plus 1 of x. So you can write this expression in this way. Now you can take this product x to the power minus n jn of x as one factor, and this x to the power n plus 1 times jn plus 1 of x as another factor. And then we will apply the rule for differentiation of the product of two functions. So you can see what will be the DC of this RHS. You can easily say that d dx x jn of x times jn plus 1 of x. Actually, I have again written the LHS, and that may be written as, you can see here, as I have told you that we should take x raised to the power minus n jn of x as one of the factors, and x raised to the power n plus 1 jn plus 1 of x as another factor. So by the rule of differentiation of two products of two functions, we can write this expression as x raised to the power minus n jn of x, and the operator d dx will be operated on the another factor. And what is the another factor? That is simply x raised to the power n plus 1 jn plus 1 of x. Now another term will be what? Now we will operate the operator on this first factor and keep the second factor at each. So now we will write this is x raised to the power n plus 1 jn plus 1 of x, and the operator d dx will be operated on what? X raised to the power minus n jn of x. You can see. And let us say this is equation 1. Now you have already studied the recurrence relation. In fact, the first and second recurrence relation we will use here to simplify the RHS of this equation 1. So you know from first recurrence relation, you can see there is a need to remember this recurrence relation to solve such problems. So according to first recurrence relation, you have seen that this is d dx x raised to the power n jn of x is equal to what? You have already studied that this is equal to x raised to the power n, x raised to the power n, and j n minus 1 of x, jn minus 1 of x. This is actually the first recurrence relation which we have already studied in the previous lecture. But here there is a need, you can see, to know x raised d dx x raised to the power n plus 1 jn plus 1 of x. We need it. So you can change in this recurrence formula n to n plus 1. So you can say replacing n by n plus 1 we get. When we will replace n by n plus 1 in this formula, you can see what will be the result. This will be simply d dx and x raised to the power n plus 1 and jn plus 1 of x, and this will be equal to x n plus 1 x n plus, actually here there is n plus 1, sorry, no, here is x raised to the power n. This is the original formula actually. So x raised to the power n. Now n will be replaced by n plus 1. So there will be x raised to the power n plus 1 and j n minus 1 is present here. So n will be replaced by n plus 1. So 1 and 1 will cancel out and there will be jn of x. So you can see when we have replaced n by n plus 1 in the first recurrence formula which I have defined here, then we get this result, that d dx x raised to the power n plus 1 jn plus 1 of x is equal to x raised to the power n plus 1 jn of x. This result has been written on the basis of the first recurrence formula. And again, you know what is the second recurrence formula. Actually, by the use of second recurrence formula, you can evaluate the value of this factor present in the second term of RHS of equation 1. So from second recurrence, first recurrence relation, you should say here, recurrence relation. Second recurrence relation reads like this. This is d dx. You have seen it already in the previous lecture. X raised to the power minus n jn of x is equal to minus x raised to the power minus n and j n plus 1 of x. Jn plus 1 of x. Jn plus 1 of x. This is actually the second recurrence formula. So if we will substitute all these values in the equation which I have written here in equation number 1, then you will actually get the value in this way. You can see here what will be actually that value. You can see here is actually d dx x raised to the power minus n jn of x and minus jn plus 1 of x. I have written this second recurrence relation. Yes, it is correct. So now we will simply use these two results which I have mentioned here on the basis of first and second recurrence relation in equation 1. And so you can see what will be actually that result. So therefore from equation 1. You can see the LHS I am again writing here. This is d dx x jn of x times jn plus 1 of x, and that is equal to, you can see the RHS of this equation here. This is in fact x raised to the power minus n jn of x. So we will rewrite it. This will be x raised to the power minus n jn of x, and the second factor is d dx this much, and see here d dx x raised to the power n plus 1 jn plus 1 of x, this is equal to this much. So instead of this we will write x raised to the power n plus 1 times jn of x. So this is x raised to the power n plus 1 jn of x, and plus, now see the second term in RHS. You can see this second term is x raised to the power n plus 1 jn plus 1 of x. First of all we will write it. So this is x raised to the power n plus 1 jn plus 1 of x, and times, you can see this d dx x raised to the power minus n jn of x, this is equal to this much. So now replace that. This will be in fact into minus x raised to the power minus n jn plus 1 of x. Now let us simplify a little bit the RHS of this equation. You can see here that this term may be written as x raised to the power minus n, and here is x raised to the power n plus 1. So this will be simply x. You can see this will be x, and jn of x times jn of x. So this will be jn square of x, you can see. And in the second term, now see, due to this minus sign here, this term will be minus now, and x raised to the power n plus 1 times x raised to the power minus n. So this will be simply x, and jn plus 1 of x times jn plus 1 of x, this will be what? This is simply jn plus 1 square of x. And so this is simply x as a common factor, take it, and this is jn square of x minus jn plus 1 square of x. And you can see this is the result which we have to prove in this second problem. Now, after solving this second problem, now see the third problem. What is the third problem? In fact, I will write this third problem again to solve it. So see this problem. This is d dx jn square of x plus jn plus 1 square of x, and this is equal to this much we have to show. So let us rewrite this problem again, and then we will solve it. So see here, our third problem is, in fact, we have to show that d dx jn square of x plus jn plus 1 square of x, and we have to show that this is equal to 2 over, sorry, 2, not 2 over, but 2 times of n over x Jn square of x minus n plus 1 over x times Jn plus 1 square of x. This is the result which we have to prove. So now we will again start with the LHS and reach to the RHS after use of the appropriate recurrence relation. You will see here. So let us solve it and start with the LHS. In fact, LHS is d dx Jn square of x plus Jn plus 1 square of x. And by the simple differentiation, you can write what will be this. In fact, Jn square of x will be differentiated with respect to x. So you know this will be simply 2Jn of x times Jn prime of x and plus. Now we will differentiate this Jn plus 1 square of x with respect to x. What will be the result? You can see this will be simply 2 Jn plus 1 of x times Jn plus 1 prime of x. This is by the simple differentiation rule, that is using the formula x raised to the power n, which is nx to the power n minus 1. You can see, and function of function. So now to evaluate this RHS, we will actually use the appropriate recurrence formula. In fact, here the recurrence formula which will be used, you have already studied in the fourth and third recurrence relation actually, because the term contains this, and such type of terms are actually present in the fourth recurrence formula and in the third recurrence formula. So let us start with those recurrence formula here. So we know from a recurrence relation you can see the utility of this recurrence relation here. So I have mentioned several times in the previous lecture that you must remember these recurrence relations. So you have seen in fourth recurrence relation that Jn prime of x is equal to n over x times Jn of x minus Jn plus 1 of x. Let us say this is equation 2. In fact, this result we should assume that this is equation 1 and that is equation 2. And also we know from the third recurrence formula, you can see from recurrence relation number 3. You have seen what is recurrence relation 3? You have seen that this is Jn prime of x is equal to minus n over x Jn of x and plus Jn minus 1 of x. This is actually the third recurrence relation which we have studied in the previous lecture. So now in this third recurrence relation, we will simply replace this n by n plus 1. Then we will get actually the appropriate term. So you can say replacing n by n plus 1. We get, you can see here is jn prime of x, and n will be replaced by n plus 1, so we will write it jn plus 1 prime of x. And in RHS you can see again this n will be replaced by n plus 1, so here will be n plus 1 over x, and since there is jn of x and now n is replaced by n plus 1, so this will be jn plus 1 of x, and plus here is jn minus 1, but n is it will be written now n plus 1, so this will be simply jn of x, you can see. And let us say this is equation number 3. So in this equation, if you will substitute the value of this jn prime of x, you can see jn prime of x, in fact this jn prime of x from equation 2 and jn n plus 1 prime of x from equation 3. If we will substitute these values, that is values of jn prime of x from equation 2 and jn plus 1 prime of x from equation 3 in this equation 1, you can see here is jn prime of x, here is jn plus 1 prime of x, and instead of this jn prime and jn plus 1 prime, we will write the expression which we have mentioned in this equation 2 and equation 3. So substituting the values of jn prime of x and jn plus 1 prime of x from equations 2 and 3 in 1, we get, you can see actually what is your first equation. You can see here I am again rewriting this LHS. This is d dx jn square of x plus jn plus 1 square of x. This is LHS. So first of all write this LHS. This is d dx jn square of x and plus jn plus 1 square of x, and this equal to, you can see the RHS. Here is 2jn of x times jn prime of x. So first of all we will write 2jn of x, 2jn of x, and then there is jn prime of x. So put the value of this jn prime of x from here, that is from equation 2. So this will be 2jn of x into this much. This is n over x jn of x minus jn plus 1 of x. Now, what is the second term? You can see here. This is 2jn plus 1 of x. So first of all we will write plus 2jn plus 1 of x. So this is plus 2jn plus 1 of x, jn plus 1 of x. And then you can see there is jn plus 1 prime of x, and we have already obtained the value of jn prime, jn plus 1 prime of x is this much. So let us substitute for this jn plus 1 prime from equation 3, and this will be what? This is minus n plus 1 over x, you can see here, and this is jn plus 1 of x and plus jn of x plus jn of x. Now we will simplify the RHS of this equation, and then you will see that after simplification we will get the desired result which we will have to prove. So you can see here. So this implies I am again rewriting the LHS. This is d dx jn square of x plus jn plus 1 square of x, and that will be equal to what you can see here. In fact, you can see this term. In fact, 2jn of x times this much. So in fact we will simply multiply the term inside the square bracket by the term outside of the square bracket, and then we will simplify it. So you can see the first term will be 2n over x jn square of x. So this will be 2n over x. This is 2n over x times jn square of x. This is the first term. See the second term. This will be in fact 2jn of x into minus jn plus 1 of x. So this will be minus 2jn of x into jn plus 1 of x. So this is minus 2 jn of x times jn plus 1 of x. Jn plus 1 of x. Now we see the second term. In fact, now this 2jn plus 1 of x will be multiplied by this, and so this will be minus 2 times minus n plus 1 by x into jn plus 1 square of x. So we will write it that this is minus 2 into minus n plus 1 over x and jn plus 1 of x times jn plus 1 of x. So this will be jn plus 1 square of x. And now see the second term. This will be 2jn plus 1 of x times jn of x. So this is simply plus, here actually will be plus, so plus 2 jn of x times jn plus 1 of x. Jn plus 1 of x. Now see, this 2jn of x times jn plus 1 of x, and here is plus and here is minus, so these two terms will cancel out. And now see, the RHS has only two terms, this term and this term, and in these two terms we can take this 2 over x as a common factor, or you can say that only 2 we take as a common factor in accordance with the result which actually we have to prove. So this will be n over x jn square of x and minus when we will take here minus sign, then there will be n plus 1 over x times jn plus 1 square of x. And you can see this is the result which in this problem we have to prove. So you can see here, this is the result. So you have seen that by the use of recurrence formula, we have again solved this particular problem. Now we will solve the last problem, that is the fourth problem which I have selected here. And so again I will first of all rewrite that fourth problem and then we will solve it. So see here, what is our fourth problem? You can see the fourth problem we have to show that j2 of x equal to j0 double prime of x. This is second order derivative of zeroth order Bessel function, that is j0 of x minus 1 over x j naught prime of x. So let us rewrite this problem again and then we will solve it. So see here, our fourth problem is what? In fourth problem actually we have to show that j2 of x is equal to j naught of x double prime. It means this is second order derivative, d2 j naught of x by dx square. This is this thing, and minus 1 over x j naught prime of x. Actually this result we have to prove. So again you can see this result can be easily solved by the use of the fourth recurrence relation. So you can see from recurrence relation 4, recurrence relation 4. What is your fourth recurrence relation? You know, I have already used this relation just now. So the fourth recurrence relation is x. I have just simplified this result. X jn prime of x is equal to n jn of x minus x jn plus 1 of x. I have slightly in fact simplified this result. And now we will simply replace this n in this equation by 1 because we have to actually find j2, so we will simply replace the we will simply replace n by 1 in this equation. You can see here, say this is equation 1. So replacing n in equation 1 by 1, we get, if you will replace n by 1, what will be your result? You can see this will be x j1 prime of x. This is equal to, now n is 1, so this will be 1 times j1 of x and minus x jn plus 1. So this will be 1 plus 1 of x. 1 plus 1 of x. And so from here you can write the expression for this x jn j1 plus 1. 1 plus 1 means 2. So let us write expression for this x times j2 of x. So you can simplify it like this. This is x times j2 of x. And what will be this? You can see we will simply take this term in LHS in RHS. So that will be j1 of x minus x j1 prime of x. So this will be, again see here, j1 of x, this is j1 of x and minus what? Minus x j1 prime of x. X j1 prime of x. So minus x j1 prime of x. And we have to find the value of j2 of x. So let us divide the RHS by this x. You can see this will be j2 of x equal to j1 of x over x and minus, here x will cancel out, so this is simply j1 prime of x, j1 prime of x. And again you can see, say this is equation number 2. Now when actually I have obtained the first recurrence relation, you can see there I have obtained a particular result. So we know it, we know that j1 of x is equal to minus j naught prime of x. You have already studied this relation in the previous lecture, and therefore if you will find the value of j1 prime of x, that is if you will differentiate it with respect to x, then that will be equal to minus j naught double prime of x. You can see. Now at the place of this j1 prime of x, from this result we can put minus j naught double prime of x. So you can use this result here, and then you will find that j2 of x will be equal to, j2 of x will be equal to, now j1 of x, you can see this is in fact minus j naught prime of x. So at the place of this j1 of x, we will write minus j naught prime of x. And here is x, so we write here x, and j1 prime of x, see here, j1 prime of x is minus j naught double prime of x. So this minus and here is minus, that will become plus. So this is j naught double prime of x, double prime of x. So you can see that j2 of x is equal to j naught double prime of x and minus 1 over x times j naught prime of x. And you can see this is your fourth problem, in which actually we have to show that j2 of x is equal to this much. So you have seen that actually in solving such type of problems, there is a very essential need to remember all the recurrence formula and the series representation of the Bessel function. So I am again suggesting you to remember all those formula. Only then you will be able to solve such type of problems in a minimum time.